MRIs could be made more efficient, possibly. I can't state this 100% fact, but there's a good chance that you could probably use gigahertz frequencies somewhere from 1 plus gigahertz, and you could probably use something that isn't harmful to the body, that won't cook you, because those are microwaves, and some frequency of microwaves, you probably want to use a low budget microwave, which is in the gigahertz range, like a computer, and you might get away with a low frequency gigahertz range to actually make MRIs more effective by some percentage, because an MRI only measures some low percentage of the total atomic material, based off of radio waves, supposedly. So those radio waves pass through the body at angles, plus they go straight through. Some percentage will be at angles, and some percentage will be by straight through electron transfer. It will swing directly through your body and go in line with the sensors and the cameras, and then they'll be able to measure a percentage of the location of a hydrogen atom. And then basically it shows some layers of the organ structure via slices, and then it does the whole body through slicing. So if you use microwaves that weren't harmful, you might be able to increase the percentage of electron transfer through the body where they bounce directly through, and that percentage, the question is the physics here, because we're getting something that comes from an atom not passing through the other side. It's coming from a center point of the body, like internally, instead of passing completely through on each side. But a radio wave of an MRI will pass in both directions as well. So technically, a radio wave from an MRI is a specific frequency that identifies hydrogen atoms. It's a unique identity. So if you were going to use microwaves, you need to know that there's also potentially a unique identity that might arise in the human body. I don't know what the actual physics of it would be. It needs to be tested. But you might be able to get an alternative frequency by using some low-budget, low-frequency microwaves that causes the body to emit a different frequency than its natural frequencies, and then you could transmit microwaves just like you would an MRI. But the only thing is it has to be a low-budget microwave, and the dosage cannot be harmful, and I don't know if it is or not. But we spend a lot of time in microwaves because microwaves are emitted already from our body. We emit microwaves. It's called infrared. And we emit higher than microwaves. We emit higher levels of energy than microwaves. But if our dosage of emission of infrared is too high, it could kill us. It could rise our body temperature up too much. So if we did that in slices, you might be able to get by with gigahertz frequencies and run it in slices, and it would pass through more readily available. But the thing is, you need an identity. what you call a physical identity. And that means that you have to arise a unique identity that comes from an event that's measured in a volume from various points. So when you do that, it gives rise to a location by measures of volume and geometry. This is how imaging really works. It gives rise to a unique identity at a geometrical coordinate plane. And then basically it tells you what the distance from that frequency based on some identity that validates that a specific condition was emitted at a rate of time from a location based on a starting phase and an ending point. And then by measuring a whole volume of coordinate plane, you can actually calculate the rate flow of a unique identity that gives rise to the identity of an atom or an electron or a molecule or a compound or whatever. And then it gives rise to what you want to see through conversion. It converts. I'm chewing on tobacco. It converts the transmission into an image. So you might try this. It might upgrade MRIs to use different techniques other than X-rays, other than MRI. You might try gigahertz frequencies. So the common ordinary frequencies for medicine